All right, now we're getting to the calculus again. Partial derivatives. What we're interested now is generalizing all that work we did in calculus with regular derivatives to functions of two variables, f and x, y, and hopefully functions with more variables as well. And the idea is going to be exactly the same in principle. We want to find out the rate of change of our function when we change, well, here's the only new part, when we change one of the variables. Back in the fall term, we had only one variable at all to worry about, so of course we were changing it as our input and asking how our function changed as a result. Now we have two variables. The way we're going to break this up is we're going to talk about the slopes when we change x only or y only. And so these are two separate pieces of information we're going to get, and they describe, therefore, the function only in one way or the other. I would need to have both pieces of information to talk about the shape of the surface. And because these individual derivatives are only telling us part of the story, they're called partial derivatives. Let's get to what these would actually mean in terms of applications or calculations with the surface. So, how do we imagine this? Well, we've got a point on a surface, very much like a point on a graph. So again, trying to think back to what we did and what we used to define derivatives in single variable calculus. So imagine a point x naught, y naught on your xy plane. We know that if we run those points through our function, we get a z value. Now the surface can do whatever it wants, but what we would talk about is a new point a little further along. So plus h, that's what this plus h is doing for us. Imagine a point a little further along, and the consequence finding the point on the surface further along as well. We can do that same transition in two directions. Okay. Now, how would we define the slopes? Well, the slope would be the delta z over the delta y in this case, if we're going this way. But that is the change in the z over, well, it's just h. Here I'm at y naught, and then I take a big step of out to y naught plus h. And in the same vein, down in the x direction, we have the x slope. Let's call it the y slope. We have the x slope, which is going to equal the change in z over the change in x. And again, that's going to be a change in z over h if we happen to define our step to be in the x direction, leaving y constant here. So we take the step just in x. We do not branch out, we do not take a step past go, we do not go out in y at all when we're doing the x slope. Likewise, when we're doing the y slope, we take no steps in x at all. It's just a step purely in the cardinal direction of y. And so that's leaving x constant. How does that play out in terms of our definitions? We're not going to spend a lot of time on this, but it's worth seeing it because it has so many parallels to what we looked at in the fall term. Notice where the h's go here. Here I have x naught plus a little step divided by that step size. That's our change in z over a change in x. And we would write that using partial derivative notation. And it's worth knowing how this is said. Let's pronounce di f, di x. Very cheery. I'm not sure what the historical source of that is, but it's a curlier d than our regular d. A regular d would look like this, and it's not that. It's a more rounded d, more like a delta, a lowercase delta. And so di f, di x is the ratio of delta z over x with the limit as delta x goes to 0. So that's what makes it a derivative, is making that step size in the denominator head towards 0. Another notation is f sub x. Sometimes it's easier to write it out that way. We'll see, we'll be using both interchangeably. And likewise, we do exactly the same thing in the y direction. Notice I'd have the point x naught, y naught plus h, so it's only a change in y in the inputs, and we interpret therefore this as the limit as delta y goes to 0 of delta z over delta y. And again, we can represent that either as di f, di y, or f sub y, whichever seems to make more sense in a particular problem. When it comes to calculating these values with a formula, we do exactly what those limit definitions implied to us. If we're taking the x derivative, we imagine that y is kept constant. So going back to the picture and going back to that last page with the definitions, we're talking about one variable changing at a time only. That's what a partial derivative is going to be all about. Let's sort of break that down to show you how that works. We have a function here of two real variables, x and y. They're both possible. It's possible to change both of them. What we're going to do is pretend for a second that we have a function of one variable only because we fixed y at some value. We said, okay, y's pinned to y naught. That's going to be something that's not going to change. So g of x is just x squared times y naught plus sine of x times y naught. And for some reason, it's easier to do the derivative here correctly. If we find notice this is a regular derivative, because, well, why? Because g only has one variable. Only has one variable. It's not f. F had two things we could change however we liked. G just has x. Oh, and this constant that shows up. Well, what does that mean? The derivative with respect to of g with respect to x, well, it's a constant, so it'll be 2x times that constant, plus, well, treat y naught as a constant. The derivative of sine anything is cos, and then we take the x derivative of the inside, and that just gives us a y naught. So I want you to just look at that form for a brief moment and go, okay, so it's 2x y naught cos blah, blah, blah. We're going to get this same form faster by just using our imagination as we go through the calculation. When we actually try to do these derivatives, notice here this is partial derivatives because f has two inputs, x and y. We're just going to treat one variable as constant, one variable as the derivative variable, simply because we can use our imaginations to do that. So because we're taking x as our variable, that means y is a constant. We're treating y as a constant. It's probably better to say it. Treat y as constant. And if that's the case, well, you just say, oh, it's x squared times a constant. So the derivative is 2x times y. So we don't have to go through that little shenanigans of y naught as a constant. No, we just say 2x times y. The derivative of sine anything is cos the same thing. And then we would just say here what we're taking is the partial derivative with respect to x of the inside chain rule, just like you know and love it. Derivative of this, y is a constant times x. We're taking the x derivative. We just get the constant back. Now, the second half of this would be, that's one part of our derivatives, the partial with respect to x. What about the partial with respect to y? Well, in this case, if we're taking the y partial derivative, we treat x as a constant. Well, let's take a look. If we have a constant times y, and we take the y derivative, we're just going to get x squared times the derivative of y with respect to y, which is 1. The derivative of sine anything is cos of the same thing, times the partial derivative of the inside with respect to y this time. That's going to give us a nice x multiplier. And that's how we would go about calculating the derivatives, partial derivatives, of any function. It's just a careful mental bookkeeping of what is constant and what is changing. And we'll practice that as we continue on through the notes.